In today's lecture, we will be going with the gate level minimization. This will be the last topic of this unit and also the last topic of this course, that is basic electronics, that we are going through. So in gate level minimization, basically we will be having a Boolean function. So a Boolean expression is there, suppose a function that is function of three different inputs a, b, c, and suppose this function is defined in terms like it is having defined in terms of mean terms. So mean terms is like 0, 1, 4, 7. So this is the Boolean function defined in terms of different mean terms. So m 0, 1, 4 and 7 is there. That means m0, m1, m4, m7. So there are four different mean terms are there. That will be summed up, means m0 plus m1 plus m4 m7. This will be defining the function f. So now to design the circuit of this minimized function, just go with the expression. Suppose ABC are the three inputs. With respect to that, m0 m0 mean term will be defining a bar, b bar and c bar, plus m1 will be defining a, b, a bar, b bar, c, plus m4 will be defining a, b bar, c bar, plus m7 will be defining a, b, c. So this is the function defined with respect to different combination of input variables a, b, c. But to go for circuit designing, for this we will be just saying like we can go with like 4 AND gates, and these 4 AND gates will be 3 input AND gates, and then finally we will be adding with an OR gate. This is how we can go with the implementation of the function. That means 4 3 input AND gates are required and 1 4 input OR gate is required for implementing this function f. But before going for implementing a function with the help of logic gates, what we do is we minimize the given function. So we will be minimizing the function. So what is the advantage of minimizing a function? Advantage is it will reduce the terms, or each terms are reduce the terms, or we can call it reduce the mean terms. We can also it can reduce the variables. So each of the variables are called literals. Okay, so it will be reducing the literals. Okay, so the advantage of gate level minimization is it will be reducing the variables or literals, and also as it is going to reduce the mean terms or literals used, it will be minimizing the or reducing the gate requirement. Okay, so whatever the number of gates required to implement the circuit, it will be going to minimize the number of gates required to implement this function f. So our main motive to use this gate level minimization is basically to reduce the hardware, to reduce the hardware or the gates. Here hardware means different gates to implement the given Boolean function. So as the function is going to be reduced based on the mean terms or based on the literals that is going to define the function, if less number of variables or less number of literals are used to define the function, that means we will be requiring less number of gates. So our main motive is to reduce the number of variables available into this function. Okay, so there are different methods to reduce or to minimize the Boolean function. So one of the method is k-map. So in this lecture basically we will be going with the k-map method. So k-map method we will be using. So here in k-map method we will draw the truth table of this function in some other way. Okay, so in truth table what we do is, in truth table what is the function we basically give is, where this function is 1 we write that, like with respect to different input combinations, what is the where is the value of function is going to be 1, that what the truth table tells us, and also tells us like at what locations this function will be 0 with respect to different input combinations. So k-map is one of the pictorial representation of our truth table only. So this k-map is also called as Karnaugh map. It is Karnaugh map. So Karnaugh map means, in short we use it like k-map. If any function is defined in terms of only two variables, then how the k-map will be defined? This A and B shows the structure of k-map for defining the k-map having a function of only two variables. So suppose a two variable is there, x and y. So with respect to that, suppose a truth table is there. So two variables are there, x and y. So total possible combinations are 0 0 0 1 1 0 and 1 1. So this is the total possible combinations if two variables are there. So with respect to that, some value of function will be there. Okay, so we basically going to have like whatever this function is there, this function will be defined only in terms of x y, different combination of x y. So different combination of x y is 0 0 0 1 1 0 and 1 1. So mean terms with respect to this will be defined like, the mean terms will be m0 here, the mean term will be m1, this is m2, m3. So if two variables are there, the maximum mean terms possible is m0, m1, m2 and m3. That means 4 mean terms are possible. Okay, so these mean terms will be defined with a square box each. So if there are two variables, 4 mean terms are there, so we will be having 4 square boxes. So one box will be explaining the defining the one mean term. So m0 will be defining, this box will be defining the m0. This is first mean term. M1 will be defining the second mean term. M2 will be defining the third. M3 will be defining the fourth mean term. So how this mean term has came? So suppose x and y two variables are there. So there is a line this make, and on vertical side x has been defined, and on horizontal side y has been defined. So once this x will be 0 and next x will be 1. So if x is 0 means it is like it is going to define, this row will be defining x bar, and if x is 1, that means it is going to define x. Similarly y, so y is 0, that means it is going to define y bar, and y is 1, that means it is going to define y. So if we want to display m0, so here x bar, or we can call it like x is 0, that means it is showing x bar and y bar, x bar and y bar is x bar and y bar is m0. For m1 it is x bar and y, for m2 it is x y bar, m3 it is x y. So that combination is similar, we can predict here. Say x bar and y bar, this is m0 defining, x bar and y, x bar and y is going to define x bar and y is going to define m1, so m1 is defined. Similarly x and y bar, so m2 will be defined. So x y bar is m2, so m2 is defined. Similarly m3, so x and y will be defining the m3. So this is how the k-map for two variables will be defined. So first we will be going with the how the k-map is presented how the K-map is designed first, and then we will be going with the solving the question related to this two variable function. So next, this is a K-map for three variable. So if three variables are there, then how the K-map will be defining? So this is, so if three variables are there, suppose x, y and z are there, so different combinations of x, y, z will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So these are different mean terms are there, m0, m1 up to m7. So different mean terms are there. So these mean terms will be defined in terms like m0, m1, m2, m3, m4, m5, m6 and m7. So how it came, we can just see here. So if three variables are there, so one variable has been put on this vertical line and two variable have been put on the horizontal line. So if one variable x is put on vertical line, so first we'll be defining x is equals to 0, that means it is going to define x bar. X is equals to 1, that means it is going, this row is going to define x. Similarly, on the horizontal part here, yz is defined. So yz both will be considered together. So yz initially it is 0, 0. Then from here to here, if it is 0, 0 means it is going to define y bar and z bar. Again it is 0, 1. So 0, 1 means it is going to define y and z, y bar and z. Next one is 1, 1. 1, 1 means it is going to define y, z. Next it is going to, it is 1, 0, so it will be defining y and z bar. Okay, so different combinations. So y, z will be having different combinations, 4 different combinations as it was in the two variable case, different combinations. So similar different combinations have been put here on the vertical side. But the point you need to observe here is, it is 0, 0, then 0, 1, then it should be 1, 0, then 1, 1, but it is 1, 1, then 1, 0. So this type of coding is called gray coding. This is the gray code. Gray code means we have already seen what is gray code. So in gray code, only one bit will be changing between consecutive numbers. So two digits are there, two gray codes are written. So in between these two, there will be only one bit change. So it is 0, 0, 0, 1. So one bit has been changed. So in between this, only one bit will be changing. So it is 0, 1, it is 1, 0. So one bit has been changed only. So it is 1, 1 is having changed to 1, 0. So there is only one bit change is there. So this is how the gray code is defined, only one bit change at a time. So between two consecutive numbers, you can say there will be only one bit changing is there. So this is the advantage of gray code. So gray code, so this one bit change means it is going to basically define like if there are two mean terms are there, in between these two mean terms only one variable will be changing. So only one literal will be changing. Okay, so either x bar, y bar and z. So in between these two, x bar, y and z. So as only y bar has been changed here to y, all are same. X bar and z are same in between these two. Any two combinations you can consider, only one bit will be changing. Okay, so this is how the definition of X gray code is going to be helping for solving the minimization of different Boolean function. Okay, so now we can see if this has been defined horizontally and this is vertically. So x bar, y bar, z bar, it is going to define m0. m1 x bar, y bar, z, it is going to define m1. But here you can say x bar, y, z. X bar, y, z means it is going to have 0, 1, 1. So 0, 1, 1 is going to define, this is m2, this is m3. So here instead of direct in continuous relation 0, 1, 2 and 3, it is like m1, 0, m0, m1 and m2 will be here, and then m3. Then from here, x is 1, y and z is 0 0, so it is 1 0 0, so it is going to have m4. Okay, so this is how different mean terms have been defined here. So for the simplicity, you can just remember like the mean terms have been defined: m0, m1, m2 and m3, m4, m5, m6 and m7. Okay, so from here, so there is a jump and shift. So uh, just take note of it. Okay, so this is very important. You need to take note of this, like it is not in continuation, it is having m0 m1 then m3 and then m2, or m0 m1 m2 then m3. This is for 3 variable k-map. Similarly, we will follow the k-map for 4 variables. So if 4 variables are there, that means if x, y, z, suppose w is there, so w, x, y, z, 4 variables are there. So total possible combinations are from 0 0 0 2 up to 1 1 1 1. That means total 16 combinations will be there. So this first term will be representing the m0, and this is going to represent m15. So 0 to 15, that is 16 combinations. So all these 16 combinations will be represented in terms of k-map. So with the help of k-map, we can see 4 variables are there. So 2 variables will be put together, and next 2 variables will be put together. So w and x have been put together for vertical representation, and yz have been put together for horizontal representation. So again, the representation will be 0 0, then 0 1, and then 1 1, and then 0 0 1 0. So that is going to follow the gray pattern, or gray code it is going to follow the gray code. Similar is here, it will be also following the gray code representation. So now if we combine w, x, y, z, so it is 0 0 0 0. So both are, all the variables are 0 0 0. That means it is going to have w bar, x bar, y bar, z bar. So it is going to define m0. Similarly, m1, then m0, m1, then m2 and m3. Okay, again m4, m5, then m6, then m7. And after that there will be a change. m8 will be defined here, 9, 10 and 11, then 12, 13, 14 and 15. So this, all the mean terms you can just get, no need to remember also, you can directly get from this terms, gray coding. So once we have made the gray coding, with respect to gray coding only the particular mean terms will be defined. So suppose randomly you select this one, so at this position it is xy, just see, this is MSB, this is LSB. So here wx is, suppose this term we want to find out. So for this term wx is 0 0 0 1, and at that time yz is 0 1. So it is 0 1 0 1. This represents m5. So m5 it will be representing. Suppose randomly select this one. So here wx is 1 1 1 1, wx is 1 1. This is MSB side. Okay, so this is wx is MSB side, w is MSB, then this is, and z is LSB. So with respect to that only we will be writing the values. So yz is there, so it is yz is also 1 1, so we will be putting y bar 1 1. So it is 1 1 1 1, so it is representing the m15. So once you have made the coding, with respect to that you can get the particular mean terms. So I think you have got the k-map, how we have drawn the k-map. And once you have gone with the k-map, now we will be using the k-map for solving the function minimization problems. So here one more point you need to write, like if a k-map is there, so in k-map the values, the k-map basically takes 3 different values. So that means different mean terms are there. So a particular mean term is in between the function. So if suppose m10 is going to be part of the function. So suppose any function is there f, it is having summation of different min terms m0, m2, m5, m10 is there. Suppose if this is the function, if m10 is defining the function, that means for m10 min term function f is 1. Okay, so function is defined, it is having a value 1 in terms of when we are going to provide mean term combination like m10. So with respect to that, in this k-map m10 box or the square will be filled with 1. Similarly, so k-map will be taking 1 or it can be filled with a 0. If suppose m11 is not in this function, m11 is not there, so we will be putting here 0. So in place of m11 we will be putting 0. And there is also a term called x. This x is called don't care. So this is new to you, I think. So don't care, x is a don't care. So don't care explains like if any function is there, if this function does not change its value or this function has no effect by a particular mean term, then we can put x, that is don't care, for that mean term. What it explains is, suppose any function is there and if this function is having a value, so for this function we can directly say like for m0 mean term the function is having one value, it is for sure. For m2 mean term f is having the value 1, it is for sure. But suppose for m8 for m8 suppose for m8 this function is not known. This means this function can have a value of 1 also or can have a value of 0 also. So if this mean term m8 is going to affect f function either in 0 way or 1 way, that means either it can have value 0 or 1, so then we place it like in don't care condition. So suppose m8 and m14 are the mean terms that can have 1 value or 0 value also, but it is not defined whether it is 0 or 1, then we call it like it is in don't care condition. So for minimization of the literals or the minimization of the function f, we can use this don't care functions also, don't care conditions also for minimizing if it is given into the question, or it is any function is there that is defined in terms of don't care values also, then we will be using this don't care condition for simplifying this function in terms of expressions. Okay, so this is the basic of k-map. Now we will see the minimization part. So in minimization part, basically we will start with, so we already know any function is there, so this function can be written into product of sum form or sum of product form. So we know SOP and POS. Product of sum of product. So if we take an example, so suppose any function is there f, that is a bar b plus ab plus a bar c, or it is a bar b bar. Suppose this is the function, it is ab is the only variable, that means it is only taking the two variables. That means for more simplification we can write like f is function of a and b. So this is the function. So this is written in terms of like it is sum of product term. So these are product terms, it is sum of product term, so it is of SOP form. So another function we can take is like, suppose any function is there, this is f1, f2 is there, that is for a and b only. So suppose it is a plus b, then a bar plus b bar plus a bar b. So this representation of the function f2 is called POS form, that is product of sum. So sum is this, and then all the sums are being multiplied. So it is a product of sum form. So if a function is written in sum of product form or product of sum form, we will be seeing like how we can simplify or minimize its get requirement, or the function, how the function can be minimized. So get level minimization will be taking place based on SOP and POS form. So first we will see if a function is defined in SOP form, that means sum of product form. So suppose if SOP type of function is there and it is of two variable, it is having only two variables. So if it is having a two variable, that means a function is there a and b, it is given like the above function we can take a bar b plus ab plus a bar b bar. So this is how the function is defined. So now we know already how the k-map is defined for two variables. So for two variables the k-map is defined like it is having four different boxes. So one variable on this side, one variable on this side. So if a is taken here, so initially a is with 0 or 1, or we can write like first term will be representing a bar and this is a, this is b bar and this is b, or this is 0 or 1. Either of these two representation we can write here. Okay, so for your simplicity you can put any value. So if this is the case, we will be seeing like how this a and b is written. So this a and b is defining the function f. So it is a bar b. So a bar b is this one. So where this mean term is there, we will be putting 1. So now we will be putting 1. ab is this, so we will be putting 1 here. A bar b bar, so a bar b bar is this, so we will be putting 1 here. So at whatever the mean term is available into this function, we will be writing 1 there if it is written in SOP form. Okay, now here, so the rule basically says is, now we need to start making the pairs. Okay, so we will be starting, if it is two variable, so we will be starting with making a pairing. So rule says make pairs. So here we need to make pairs. So pairing will be done either in horizontal or in vertical only. Okay, so we cannot take diagonal pairing, only horizontal or vertical pairing is allowed. So here we will be making the pairing. So pairing of 2. So pairing can be done, pairing can be done of either two mean terms, vertical or horizontal, or four mean terms, vertical or horizontal, or 8 mean terms, or 16 mean terms. We can take this type of pairing. If suppose there is no pairing, then also we will be considering that mean term only. Okay, so if one pair we have made, if there is a possibility of making the another pair, even though the this mean term is being repeated for making the pairing, then also we will be making the pairing. So this is another pairing. So with respect to first, we make the pairing. So once we have made the pairing, with respect to that, what will be the variable, what will be the literals that will be explaining this mean terms, we will be writing. So function f, now after making the pairing, we will be minimizing, we will be writing the variables that is going to minimize while solving for this minimized or reduced variables. So here, this for this pairing, whatever this variable is there, in this variable is a bar, so we will be writing a bar multiplied by the variable coming here. So this is taking those two, so b plus b bar, so it is going to be like b bar plus b, so a bar multiplying b bar plus b plus, so this is, so the expression with respect to this color, so here one is there, one is there, so b bar is there, or we can just take the vertical side, so this is a and a bar is there, so both are there, so a plus a bar will be there multiplied by the variable that is across this vertical line, that is b, so this is b. Now we will solve it, so it is a bar, now it is b bar plus b, b bar plus b is 1 plus a bar and a bar and a, if we add it or and it will be 1 dot b, so it is a bar plus b. So after simplification, this function has become a bar b. Okay, I hope you have got. So first we need to draw the k-map, then we need to put the mean terms there, and then after putting the mean terms, we need to make the pairing. So make the pairing is, so pairing will be done either possible pairing of 2 mean terms or 4 mean terms, 8 or 16 mean terms. So for 2 variables only 2 or 4 will be allowed. So suppose any function is there, so just take another question. Suppose a function is there such that it is having, this is a bar, a, b bar and b, and this function is defined for all the mean terms, that means it is defined like that. So here we should be making the pairs, so pairing should be done either pairing of 2 or pairing of 4. So if pairing of 4 is being observed or the pairing of 4 is available, we will be making the pairing of 4, we will not doing the making of pairing of 2, so we will do the pairing of 4. So if we do the pairing of 4, then the function that is a and b variables are there, so we can just write like a plus a bar, a plus a bar multiplied with b plus b bar. So from there a plus a bar is 1 multiplied by b plus b bar is 1, so overall it is 1, that means this function is including all the mean terms, so this function will be defined by 1. So if all the mean terms are defined within a function, that function will be equals to 1 itself. Okay, and if suppose any function is there that is having only one, or suppose a function is there, it is b bar b, a bar a, suppose it only takes two mean terms, and these mean terms are here and there, so these are the mean terms. So with respect to that, there is no possibility of pairing, we can't do pairing, vertical pairing or horizontal pairing, because there is no one here or no one is here. So for this also we can't do any vertical pairing or any horizontal pairing, so there is no one available here and here, so there is no pairing possible. So whatever this function is there, so that function will be defined by like, we will be making the pairing of 1 itself, so we will be making the pairing of this only and this only separately. So with respect to that, if we make the pairing here, so it is going to do the expression is like a across this one a, and vertically it is b bar, it is a dot b bar will be there, plus this is going to give a bar into b, a bar into b. So the function that is explained by it is a pre-minimized, you can say. So there is no need to minimize this function because it is already a minimized function. For 3 variable function, we will be taking an example. Suppose example is 3 variables means abc is the variables. It is defined like a bar bc plus a bar c bar, a b bar c bar plus abc plus a bar c. Suppose this is the function and we need to draw its k-map. So for 3 variables, the k-map is defined like that. So one variable we will be taking on vertical side and 2 variables like b and c we can take on the horizontal side. So it is 0 0 0 1 1 1 and 1 0. Here it is 0 and 1. So with respect to that, it is a bar bc means 0 1 1 is there, 1 0 0 1 1 1 1 0 1. So it is m3 m4 m7 and m5. So we can take that also. We can put 1 where this function is min term is available. So it is 0 1 1 is here, so 1 will be here. Next is 1 0 0, it is 1 0 0, this one is there, 1 1 1, all are 1 here, 1 0 1, so 1 0 1, it is this. So this is the min term representation. So there are 4 terms, so 4 terms are here also. Okay, now what we need to do? Now we need to do pairing. So pairing, first of all we will be searching for highest pairing. So highest possible pairing that we can do is 2 only here. So here one pairing will be this one and another pairing we can do is this one. So we need to make the pairing so that all the mean terms is covered. We can't left any mean term without a pairing. We have to make the pairing if the pairing available. If there is no pairing in the previous case, like, so there was no chance of pairing, so we have not done any pairing. But if there is a chance of whatever mean terms available, we have to make the pairing. So maximum possible pairing is 2 mean terms only. So with respect to that, now we will be starting with the expression. So it is for this pairing, this one is defined by a, this is a bar. So if it is a, so we will be writing a into these two. So these two are available, so in between these two whatever is the common we will be taking. So common means it is 0 0 means it is b bar c bar, it is b bar c, it is bc, it is bc bar. So in between these two whatever is the common, so we have already seen in the previous cases, like what we were doing is basically we were considering both. So b bar and b we have added, okay, or if this is the case, here it is again adding. So just go with the full method, like a bar a dot, then we will be adding these two. So it is b bar c bar plus b bar c plus, for this term it is like b c or bc multiplied by these two terms will be added. So 1 a plus a bar. So it is a, if we simplify it, b bar we can take common, so we can take b bar common, so it is c plus c bar plus here bc, a plus a bar is 1, so it is 1. So it is coming out like a dot b bar. So c plus c bar is 1, so we need not write. So this is the simplified one. Okay, so in shortcut also we can just write, so we need not to follow the step again and again. What we can directly write is from the expression itself we can write, if this is the mean term, with respect that it is A. So A will be there. In between these two, we will be taking the common. Which one is the common? So B bar C, B bar C, B bar C bar, B bar C. So in between these two, common is B bar. So we will be taking A dot B bar plus. Next one is, in between this we have to take BC. So BC will be as it is, and here if these two both terms are added, means A bar is added, that means it will be 1 again. So it is A, the same will be there. So if both terms have been included, means A plus A bar will be there. So A plus A bar is always 1, so there is no need to consider. We need to consider only this part then, if both have been included. So this will be the answer. With respect to that, we can get some conclusions, like we can conclude some point. So conclusion is, if only one square is there, if only one square is there, then it will be representing one min term. So one square is representing one min term, one square is representing one min term. If we have made the pairing, instead of two min terms, we are reducing one min term. Only one min term will be represented. So if we make the pairing of 4, so instead of 4 min term, it will be reduced to 1 min term. Okay, so this is how we do the pairing, and the pairing affects the reducing the mean term. So here conclusion we can just made is, if one square is there, so it will be representing one mean term, and in case of 3 variable, this one mean term will be giving you out 3 variables or 3 literals. Second we can conclude is, if 2 square is there, so this 2 square will represent 2 square will represent 2 square will 2 adjacent two adjacent squares are there. It will represent one mean term only, but it will be giving only 2 variables. If 3 no, there will be no 3, it will be 4. If 4 adjacent squares are there, it will basically represents one mean term. This will be giving only one variables. Next is like, if 8 adjacent squares are there, it will be representing one mean term, and it will be giving no variable, or it will be giving function is equals to 1. So we have already seen this is the case of 3 variable case. So if it is 2 variable case, if all are 4 all 4 variables are there, 4 mean terms are there in a square, that means in 4 mean terms we have considered for the case here. So 4 distant squares are going to give one variable in case of 3 variable case, and 4 squares pairing is going to give 1 for the function in 2 variable case. A similar conclusion we can make in the 3 variable also. So this is the conclusion. Next we will see some questions based on that. So we have just seen one question, so we will further check for another questions, like if suppose a function is given a b c, so it is a bar bc plus a bc b bar c bar plus A B C A bar C. If this is the case, we can define A bar A, this is BC bar B bar C, BC this. So now we can just write A bar BC. A bar BC is this. Yes. A bar BC is this one. 1 A B bar C bar A B bar C bar A B C A B bar C A B bar C. The previous question was the same. Yes. Okay. So I have seen, yeah, this was the case of previous question also. Okay, we can just, okay, so no problem. So we have seen this. So one point we can see here. Yeah. So pairing we have made here and here. But one thing we can see is there is a possibility of pairing to this also. There is a possibility to have a pairing of this also. So this pairing, so we will be making sure, right, like all the mean terms should be included while doing the pairing. So by doing these two pairings, we are able to consider all the possible mean terms into this pairing part. So there is no need to do this extra pairing. So if we do extra pairing, extra term will be there into the function. So this extra pairing that is not required is called redundant. This is called redundant pair, or we can call it a redundant term. This is called redundant term. So there is a redundant term also, and these are the essential terms. Essential pairing is there, need to be done. So this essential pairing is called essential prime implicant. So these are required. So these are called essential prime implicants. Essential prime implicants. And each mean term is called one implicant. Okay, so there are implicant. So each mean term will be representing one implicant. So there are four mean terms, so four implicant will be there. And essential prime implicants means those pairings that are must to consider all the possible implicant or mean terms. And one also term is there called prime implicant. These are redundant term, or we can call it like this is, there is no need to write mean terms with respect to that because it is redundant. One is called prime implicant. So prime implicant is basically indicates a product term basically that is obtained by combining the maximum possible number of adjacent squares. So maximum possible number of adjacent squares by combining any number of adjacent squares. If we are going to make a pairing, whatever the possible pairings can be done, that is called prime implicant. Okay, so here we can see the pairing can be done this way, and one more pairing is, that is redundant term will be there with respect to this pairing, but there is a chance of pairing. So the all possible type of pairing that can be there, that comes under prime implicant. So there will be one pairing, second pairing, and this is the third pairing. So prime implicant here will be 3. Okay, so in sometimes in gate questions also, or PSUs, this type of questions is asked, like how many prime implicants are there, how many essential prime implicants are there, or how many implicants are there. So implicants means whatever the mean terms are there, all are called implicants. So there are 4 mean terms, so 4 implicant will be there. Prime implicants are whatever the possible combination of pairing is there, that will be called prime implicant. So there are 1 pairing, 2 pairing, and 3 pairing. So there are 3 possible pairings are there. So that's why it is 3 prime implicant. But there is some essential pairings are there. So that means we need to make this for sure. So to consider this one, we have to make this pairing. Okay, so to consider this one, we have to make this pairing. Okay, that means these two are the essential one, and this one is not essential. So out of the prime implicant, only 2 are essential. So essential prime implicant will be 2. So always prime essential prime implicant will be less than or equal to prime implicant. So prime implicant will be considering the extra terms also, that is possible, but there is no use of that, then also that will be a prime implicant. So up to here we have solved some 2 variable and 3 variable function related minimization problems. If we are going to solve minimization related problems, we have to follow certain procedure. So that procedure we will see now. What are the different procedures are there? So these procedures include, the first step is, first of all we will be searching for an octet. Octet means the maximum possible the maximum possible in case of 3 variable. So if a 3 variable is there, the maximum possible pairing that we can do is, if all the squares have ones. If all the squares is having 1, then maximum pairing that we can do is of 8 squares. So that is called an octet. So we will be searching for octet first. Okay, so what is the advantage of opting for octet? It is, it eliminates all the 3 variables. If an octet is there, it will be eliminating all the 3 variables. There will be no variable, that means the function will be equals to 1. Okay, so the advantage of octet is it will eliminate 3 variables. The second one is, after octet we will go for quad. Quad means 4. So now the quad means 4. 4 means if 4 squares, 4 adjacent squares are having 1, so we will be searching for a 4, making a quad. If quad we are able to make, then it will eliminate, here it was eliminating 3 variables, so the quad will be eliminating 2 variables. Eliminating 2 variables means out of A, B, C, 2 variables will be removed. That means only 1 variable term will be left. Okay, so the next one is third one. Once we have opted for octet, there is no octet, then we will be searching for quad. If there is no quad, then we will be going with the pairing. Now we will do the pairing. So pairing will be of 2 mean terms, 2 adjacent squares. So basically this eliminates it will be eliminating 1 variable. That means 2 variable term will be left after reducing this paired term. Next one is fourth. So suppose we are having the fourth term. So this fourth term is basically going to get like, once we have done the octet, quad and pairing, now we will be going with single term. So here we will be looking for any single term is there or any single mean term is there. Okay, so if we are having any single term into our K-map, then it will not be eliminating any variable. So here no variable is eliminated. So as it is unable to eliminate any variable, so uh, we will not be considering single term. We will be basically searching for either pair, quad or octet. If octet, pair, quad and pair is not available, then we have to make the single term. We will be considering single terms. Okay. The next is remove any redundant term is there. So if any redundant term is there, we have to remove that. That means we need not to include into the expression of the function. So if we are going to consider the redundant term, then there will be the possibility like instead of reducing, we will be able to increase the variable or increase the gate requirement, logic gate requirement for implementing that particular function. So we will be basically removing the any redundant term that is available into the key map. So now once we have gone with these terms, we will take some examples further. So just consider any function f is there that is represented in terms of 1, 3, 6 and 7. So here it is very easy to solve. Okay, so we will be able to solve it easily by using the method that we have seen. Okay, so we will be drawing the K map. So into that K map, three variables are there. Suppose A we have considered here, so it is 0 and 1. B, C we have considered here, so it is 0, 0, 0, 1, 1, 1, 1, 0. So here this indicates 0, 1, 2 and 3 mean term. This is 4, 5, 6 and 7. So it is 1, 3, 6 and 7. So 1 means here we have to make 1 is there, 3, 3 is here, 6, 6, 6, 6 is here and 7, 7 is here. Okay. So now we need to do the pairing. So pairing, suppose we have done the pairing here. Then if we do the pairing here, suppose we have done the pairing here. And now we need to write the function. Suppose we, and this is separate, this is separate. Now we want to write the function. So function will be, this is separate, this is separate. We have not done the pairing. So if we are going to write here, so it will be a bar, this is b bar c. So it will be a bar b bar c plus. In this case, this is both are there, so it will be a plus a bar will be 1 multiplied by bc. So it is bc plus. This term is a dot, this is bc bar. So the function is having a bar b bar c plus bc plus a bc bar. So this was the 1. So suppose we have not the pairing like that. We are going to have the pairing in some other way. So suppose some other way is like, suppose this is the pairing and another one is this one. So first of all we will be searching for pairing of octet. So octet is not available. We will be searching for pairing of 4 terms. So there is no 4 squares that is having 1. So quad is also not possible. So now we will be searching for pair. So pairing we can then do here, or we can do here, or we can do here also. Okay, so if suppose we have done the pairing here also, extra pairing, we have done this also. So there are 3 different pairings we have done. So with respect to that, if we write the function, so now the function will be, with respect to that, it is a bar multiplied by common between these two. So common is this one, the last term, the c term is common, so it is a bar c plus. This is there, so it is both terms are in a and a bar plus will be added, so it will be 1. So 1 dot bc, 1 dot bc plus. For this term, it is a dot common between these two. So common between these two is b. So a dot b. So it is a bar c plus bc plus AB. So this is the case. Suppose we have uh, one thing from there we can just see like this the pairing done by this color, this pairing was not required basically. Even without this pairing also we are able to just two here. Okay, so without this pairing also we are able to consider all the implicants or all the mean terms. So we are able to consider all the mean terms. So with respect to that, the new function, if we want to write like here, with respect to that it will be a bar and c plus with respect to that it is a into b. So compare all the functions. So if this was having three different terms, so that means extra required gates will be required, and these three different variables are there. It is also in three different terms, so extra gate is required also to implement. So it is having minimum number of terms. So minimum number of terms means it will be requiring less number of hardwares to implement the same function. So this is the most preferred and it will be the correct one, the simplified. This is not the simplified one. So in between these two if we compare, it is having a redundant term. Okay, so that redundant term here is this one BC. So BC was generated because of this only. So that was the redundant term. So we should be minimizing the redundant term by not considering the that particular term.